Thank you for coming to World Metrology Day. I'm Peter Fisher. I'm the head of the physics department. I was going to count this event a success if 50 people showed up, so thank you. To start, I'd like to thank Ryan Higgins and Christina Andujar in the physics headquarters who did a lot of the work to make this happen on pretty short notice, and the MIT News Office for their help putting this event together and getting the word out. So today is an important day as new definitions of several of the base units of measurement come into effect, and Professor Wolfgang Ketterle is going to tell us about it. He's probably uniquely qualified in this regard. Professor Ketterle studied physics at the Technical University of Munich and the University of Munich, receiving a PhD in 1986. Following time at Max Planck Institute in Garching and Heidelberg, he joined the MIT faculty in 1993, where he now holds the John D. MacArthur Chair in Physics. In 1985, he was among the first to observe a singular quantum mechanical effect in which a large number of atoms coalesced into a single quantum mechanical entity called the Bose-Einstein condensate. And this opened a new field that impacts precision metrology, quantum computing, foundational quantum mechanics, and a host of other areas. Groups worldwide have adopted and developed this new tool arising out of Bose-Einstein condensates, and the MIT group continues to lead this field. For this work, Professor Ketterle was awarded the Nobel Prize in 2001, along with Eric Cornell and Carl Wieman, as well as the Rabi Prize, the Franklin Prize, and a host of other prizes. He is a remarkable teacher as well and has won the School of Science Teaching Prize. So please welcome Professor Wolfgang Ketterle.
Good afternoon. I think it's a special event today, and what I want to talk about is something really important. As of today, the world will never be the same, because the unit, the fundamental definition of the kilogram has changed, and that should affect all of us. What is all fundamental units as of today, time, length, mass, and charge, are now defined by fundamental constant and no longer by man-made artifacts. And that means, for the first time in mankind, we can communicate our fundamental units, our system of measurement, to aliens without exchanging artifacts. Now, if you think aliens and extraterrestrials is the fashion of today, that's not the case. Let's go to Max Planck and to his famous paper in 1899, where he thought about fundamental constant. And you see what I've underlined. He thought that we can define units by fundamental constants for all times and all cultures, including außerirdische, extra-human cultures and außermenschlich, extraterrestrial and extra-human. This is what Planck had in mind more than 100 years ago. And as I will tell you at the end of my talk, we are realizing now Planck's vision, but not completely. So why May 20th? May 20th is World Metrology Day. It's an annual event that we celebrate metrology in the world, because it was on May 20th in 1875, 145 years ago, that the Meter Convention was signed by 70 nations with a goal to have worldwide uniformity of measurement. So we could celebrate World Metrology Day every year, but this time it is very special because, as I want to tell you, what has happened with fundamental constants and measurement is the most significant change in the last 100 years. And this change was triggered by the General Conference on Weights and Measures. They met in November 2018 and unanimously passed the new definition of those units. And they decided that the new units will go in effect, will become law today on May 20th. This is actually a rare example where all countries in the world were able to make a unanimous decision. So the new units, and you see the SI units on the outer circle, they are now defined by fundamental constants on the inner circle. So there are changes for several constants, but the real important one is about the kilogram. So therefore, 90% of my talk will be about the kilogram. As you know, mass was defined with this Urkilogramm, le grand K, the original kilogram, and all precision measurements of masses were eventually traced back to a comparison with this piece of metal kept very safely in a vault in Paris. This piece was created in 1889, and it will be, well, maybe not dead, but retired today. It will completely lose its function and become a museum piece. And why? Well, because it didn't behave well. When comparisons were made between the kilogram and copies of the kilogram, or among copies of the kilogram, people found that the kilogram was drifting up and down about 10 microgram. 10 microgram is 10 to the minus 8. So metrology of masses was limited to 10 to the minus 8 because this piece of metal, even with the greatest care in keeping it, cleaning it and such, was not reproducible. Possibly because maybe there were some hydrogen atoms diffusing out of the material, or there were some surface layers. Nobody knows why the drifts were there by 10 microgram. So the new definition of the kilogram is given here. I took it from the official website, and there are two things I want to highlight. What appears here is this number, 1.5 times 10 to the 40. It's not so often mentioned in other people's presentations about the new SI units, but this number, which appears here, 1.5 times 10 to the 40, will actually play a big role in my talk. And then, finally, how do they explain the kilogram? The effect of this definition is to define the unit, this is the unit of action, and together with the definition of meter and second, you get the kilogram. Do you understand that? It's a dimensionless analysis. We define the action with help of h, and now we pull out the kilogram. And actually almost all articles, websites, popular articles, publications say the kilogram is now defined in terms of the Planck constant, but they're not explaining how. And this is actually the reason why I got into it. I've never done a metrological experiment. I've nothing to do with a new determination of the Planck constant, of the kilogram through the Planck constant. I just felt we have to explain it better. When I ask, well, several are in the audience, my graduate student, can you explain to me why h defines the kilogram? They were not able to explain it to me. Then I asked my colleagues. Many of them were not able to explain it to me. And so I felt I had to step up and explain it in the fundamental way with sort of the same rigor as I'm thinking about physics as a fundamental physicist. So I try to explain the kilogram in a different way. I'm not defining it differently, but I'm formulating an explanation in a different way than I think you will see anywhere else. So some people even get it wrong. Here, the kilogram is defined in terms of an electric current. I think that people got confused. As I will tell you later, the kilogram can be measured with a watt balance, and in a watt balance you have currents. But this is not the definition. This is the realization of the definition, which is very different from the conceptual definition. Or the German PTB, the German National Institute of Standards, or NIST have extensive websites, have materials for teachers how to teach about the kilogram, but they're not explaining it well. They're rather saying, well, these are the two equations which have h and mass in it, and it is counterintuitive, which means we're not explaining it, that mass is now related to h. Or here, PBS said it is now much more abstract. The old definition, there was a real object, but now it is much more abstract. Or look here, this is the PTB, the German National Metrology Institute, wants to explain the new SI in schools. And what they say now is all quantities in mechanics, which are in the units of time lengths and mass, are now represented by constants of frequency, the cesium frequency, speed of light, and an action. So what happens now is we have to represent the world of physics in a new coordinate system. And they say this is a challenge for students, but it's also a challenge for the teachers to explain it. Or here is a recent write-up where they repeat the definition, how the kilogram is defined now in terms of Planck's constant, but then they challenge, well, me, try explaining that to someone. And finally, this is the press release from last week from the German Metrology Institute. It's a fantastic institute. They do fantastic outreach. But look what their press release says. If you come across someone who can tell you by heart and without cheating what a kilogram is, beware. It's probably a weird scientist or somebody who is completely enthusiastic about the fundamental units. So, I'm not reaching the goal of my talk. If you cannot go out to the street and tell even non-physicists what the new kilogram is. So this is the goal I want to accomplish today. So here is the definition in one picture and one sentence. 1 kilogram is the mass of a fixed defined number of photons at the frequency of the cesium atomic clock. So if you have an empty microwave cavity and a microcavity filled with this number of photons at the cesium frequency, the difference is exactly 1 kilogram. And this number is simply the product of defined fundamental constant. H is defined, has no uncertainty. C is defined, and the cesium frequency is defined. So this is now a defined number, and I showed you before the same number appeared on the official website of the Bureau of the Office for Standards and Measurements. So this is, if you're happy now, this is one of the main messages of my talk, but I know it raises questions. One is, what is the mass of the photon? There are some people who have told me photons don't have a mass. So this needs explanation. And the other thing is, 10 to the 40 is a big number. How do you count 10 to the 40? So I will spend a lot of time in my talk explaining those two things. But before I do that, since it's not just about the kilogram today, I want to point out that mankind has advanced in the definition of units. We were using for a long time imprecise natural objects, like the revolution of the Earth around the sun, which is not terribly precise as we know now. Or we used man-made objects, like the meter stick or the original kilogram in Paris. But as of today, we only use perfect microscopic objects and fundamental constants. And let me just illustrate this by looking at how the definition of second, meter, and kilogram have changed. So the second was first defined through the mean solar day, but then people realized that how the Earth rotates around it and what defines the solar day has more fluctuation than the year, how the Earth rotates around the sun. So this was changed, and it was only since 1967 that we got away from the astronomical definition and defined the second through the frequency of the cesium atomic clock. The meter was also first defined through a naturally occurring object, the Earth. It was defined as 1/10,000,000th of the distance between the North Pole and the equator. So it was defined as 10/10,000,000th of the quarter meridian, of course the meridian which passed through Paris. But people felt also this was a natural definition and everybody could have access to it. It's really difficult to measure that, and there were whole expeditions who measured the meridian of the Earth. So therefore, rather soon, it was replaced by a man-made prototype, a special-made meter stick, which was kept in Paris. And eventually in 1960, we advanced from a man-made object to an object made by nature, namely the krypton-86 isotope. It emits a certain color of light, red light, and the meter now was defined as a certain number of wavelengths at the krypton emission. So this was already fulfilling pretty much all requirements. It was a perfect nature-made microscopic object, but eventually some years later, it became advantageous to not refer to krypton again to another species, but rather say in a universal way, 1 meter is the distance traveled by light in a certain amount of time. And this is the current definition of the meter. The kilogram started out first with an object made by nature, water, and the kilogram was defined as the mass of 1 liter of water at 4 degrees centigrade. But you know, water is not water. It's purer and such. It's really difficult to precisely match that, especially if you want an accuracy of 10 to the minus 8. And then people built prototypes, and eventually those prototypes allowed mass comparison at the 10 to the minus 8 level. And now, of course, the big day today, the kilogram is defined by the mass of 1.47 times 10 to the 40 photons. So, but let me point out and let me give the simple message. A lot of people say the definition of units through fundamental constants is more complicated. If you define the length by a meter stick, nice. But if you define length by speed of light, it gets a little bit more indirect. Also, you can quickly explain a meter is how far light travels in a certain fraction of a second. But I try to give a uniform message that all SI units, or those one here, are defined in a defined number of fundamental particles or phenomena. 1 second is an exact number of the oscillations of the cesium atom. 1 meter is 30.6 times the distance light travels during 1 oscillation of the cesium atom. So there's a fundamental length which is defined, the distance light travels during 1 oscillation of the cesium atom, and the meter is a multiple of it. What could be simpler? Or take the coulomb, the unit of charge. The coulomb is now defined that it is so and so many times the elementary charge of the electron or the proton. What can be simpler? You define a unit by a defined, specified number of elementary units. And now the kilogram follows that. It is the mass of 1.47 times 10 to the 40 photons at the cesium frequency. So everything is now defined by the cesium frequency and fundamental constants, the speed of light, Planck's quantum, and the elementary charge. So the question is, why didn't we define mass earlier by an atomic or elementary particle? I told you that 50 years ago people said the length can be measured in the wavelengths of the resonant emission of a certain atom. Time could be defined by the frequency of an atomic clock. Why didn't we simply say 1 kilogram is so and so many times the mass of the carbon-12 atom, or so many times the mass of an electron? We could have defined it long time ago, but it would not have made sense. For the following reason. When it comes to big objects, we can compare them with scales, and we can do a comparison at the 10 to the minus 8 level, which is actually not bad. If we have microscopic masses, the mass of the electron or the atomic mass unit, the mass of atoms, we can actually do comparisons of 10 to the minus 10, sometimes even 10 to the minus 11. But the problem is to connect the two. And if we had defined a few years ago the mass, the kilogram, through a microscopic definition, which could be specifying the mass of the electron, specifying the mass of the carbon-12 atom, or specifying age, which is very similar. It is a microscopic definition. We would not have been able to take the microscopic definition and measure something big and say this is now 1 kilogram with a precision of 10 to the minus 8 or better. So we would have actually lost out on the macroscopic masses. We would have lost the 10 to the minus 8 precision if we had done a microscopic precision earlier. But now, and you may have heard about it, thanks to the amazing technological advances with two methods, the silicon sphere method and the Kibble balance, I will describe both later in my talk, we have now this connection at 10 to the minus 8. And now we can have a microscopic definition. We still have the same precision in creating kilograms and combining kilograms, but we have lots of advantages because our definition is microscopic. So it was only now that we had reached that we had met the technological challenge of comparing a microscopic mass to a macroscopic mass at 10 to the minus 8 precision. Okay, so let me now come to the question, what is the mass of photons? And I have to tell you, when I started to go around and tell my colleagues, the kilogram is defined by a defined number times the mass of the photon. There were famous colleagues who said, no, you can't do that. A photon doesn't have mass, a photon has only energy. So for me, but now, this is an opportunity. It is an opportunity that I can educate the public, maybe educate some of you, what the mass of the photon is. So, but let me first bypass. I don't really need photons, because what I can do is, I can, instead of 1.5 times 10 to the 40 photons, I can take 1.5 times 10 to the 40 cesium atoms. Here, I put them into the excited hyperfine state, where the nuclear spin and the electron spin are parallel. And here, I put the cesium atoms in the ground hyperfine state. And because the excited state is more energetic, those cesium atoms have more mass. So if you want to eliminate the word photon from the definition, I can say 1 kilogram is the difference in mass of 1.5 times 10 to the 40 cesium atoms, which are either in the ground or the excited state. So I don't need the photon, but hey, we are physicists, or many of us, we love the photon. But let me first point out what I just said, namely that excited cesium atoms have more mass than ground state cesium atoms. Some of the most precise tests that binding energy or excitation energy corresponds to mass was actually performed by Dave Pritchard here at MIT. There is a reaction that a 32 sulfur isotope does neutron capture and goes over to 33 in the gamma ray. So you would think, if you just think in classical rest masses, that 32 sulfur and a neutron should have the same mass at 33 sulfur. But the gamma ray which is emitted means there is energy escaped, and this is heavier than that. And by doing precision mass spectrometry at world record precisions, 10 to the minus 8 precision, in the 10 to the minus 10 or 10 to the minus 11 precision, Dave Pritchard and his collaborators were able to verify that what he measured as a mass difference was measured by NIST by precisely measuring the wavelengths and therefore the energy of the gamma rays, and it added up. So therefore, you can't just add rest masses. The binding energy or the excitation energy becomes gravitational mass. And this has been determined here. Okay, but now let's talk about the mass of photons. The photon has, things can get a little bit confusing because in special relativity, we can talk about the rest mass, and this is maybe the most solid way how we should use the word mass. But then there's also the concept of relativistic mass. And then there is the concept in particle physicists of the invariant mass. So mass is not mass, and we have to pick our words carefully. So the word relativistic mass, which many textbooks now avoid, is just the energy equivalent. You take whatever you have, whatever it's its energy, divided by c squared, you get something which has the unit of mass, and this is relativistic mass. But maybe the more important mass, the mass which you can put on a scale, is the rest mass. And of course, the photon has no rest mass. We all know that. But now just bear with me. I know for the non-physicist, who's actually not a physicist here in the audience? Wonderful. I try to really keep 80% of the talk for you. Here is now 2 minutes for the physicist. And that's the following. Assume we have a relativistic energy momentum 4 vector, and we are in a frame where the total momentum is 0. So you have an arbitrary system, but the total momentum is 0. But there is energy. And now you do a Lorentz transformation, and you get this 4 vector. And if I expand it, it becomes this. So no matter what my system is, I started in a center of mass frame, I do a Lorentz transformation with a small velocity v, and I find, now viewed from the moving frame, the system has momentum, which is a mass times velocity, the Newtonian expression, and the energy is the original energy plus 1/2 mv square, the Newtonian expression. And the mass here is nothing else than the energy divided by c square. So if I have any form of energy, but I'm in a frame, but there is a frame where the center of mass momentum is 0, then this whole object, when observed from a frame with a small velocity, behaves like a classical object with classical momentum, classical kinetic energy, and the mass, the rest mass of the system is simply the total energy divided by c square. So this is mathematically exact. So that's what I just said. So let me just give you examples. If I have one photon which forms a standing wave in a cavity, and let me idealize that the cavity mirrors have 0 mass, then this is a system which has a rest mass of h bar nu over c square. The relativistic energy of the photon becomes the rest mass of the system, because if I take this system and move it with a velocity v, it has momentum mv and has kinetic energy 1/2 mv square. It's real, it's a real mass. Or without mirrors, if you have 2 photons which are emitted in opposite directions, they have a rest mass of 2h bar nu over c square. This is often called the invariant mass in particle physics. Or if I take many photons in a cavity, and this is my formulation of the definition of the kilogram, the cavity has now an extra mass of the number of photons times the energy of the photons divided by c square. So this is real mass in every sense of the word. This is rest mass of this standing wave cavity, rest mass of this microcavity which has stored the photons. Since I was just teaching 8044 statistical mechanics, who are actually some students, undergraduate students who took it? Wonderful. So maybe this is for you. If we have a gas and one is hotter than the other one, the one which is hotter is heavier because it has more energy, and therefore the rest mass of this box is higher than the rest mass here. So in other words, what I'm telling you, for any system where the center of mass moment is 0, we need a rest frame. I mean, you can put something only on a scale if you can put it to rest. So if you can put the system to rest in a rest frame, then the rest mass is the sum over all relativistic masses, which includes all the energy, kinetic energy, photon energy, everything which is inside, and it is definitely not the sum of the rest masses. I'm just reminding you of the basic way how energy and mass works in special relativity. So I think now I've really fully explained to you that yes, these photons really give their mass to the cavity, and it is mass which you can weigh, you can accelerate the cavity, and in every sense of the word heavier, the cavity is heavier now. Okay, this is a general proof. I just used 2 lines of equations with the relativistic energy momentum 4 vector, but I always want to, intuitively understand things. So let me now explain to you microscopically where does the mass of the photon come from. So let's assume we have a cavity where photons go up and down. And now just to have a frequency reference, I assume there is a source which emits photons at the frequency nu, and this source is positioned in the lower mirror. So if I now go to a moving frame, the cavity is moving, and that means from the lab frame, the cavity is moving now, and from my lab frame, the cavity is moving, and the photons, in order to stay in the cavity, have to bounce at an angle. So there is a small angle, which, of course, I exaggerated in this drawing. This angle is V over C. But that would mean now, in the horizontal direction, there is momentum, which is what I say the mass of the photon is defined by V. And now I can ask, what is the frequency? What is the energy? Well, because there is now an angle compared to the source, I measure a first-order Doppler shift. But because of time dilation, I also measure a second-order Doppler shift. And if I put the two together, I find that the energy of a photon as viewed by the moving frame is the original energy plus m naught times v square over 2, like a classical object of mass m. So in other words, I've explained it to you already on the previous slide with the 4 vector, but now you understand microscopically the inertial mass of this stored photon, or its inertial mass gives rise to kinetic energy. It takes inertia, there's inertia, you have to provide energy to accelerate it. This inertial mass of the photon, as you see here, mv square over 2, is due to the relativistic Doppler effect. What about the gravitational mass? Well, the photon is bouncing up and down in this cavity, and every time 8044, if a particle hits the surface, there is a change in momentum, and this is what causes pressure. So the photon creates sort of pressure, but since it bounces up here and there, the outward force on the upward force and the downward force are the same, as long as gravity is 0. But now let's switch on gravity, and we have the gravitational redshift. Now the frequency of the photon up there is a little bit less than the frequency down there. So now I can calculate the force. The force on either of the mirror is the momentum transfer, 2 times momentum transfer over this is 2h bar k, the momentum transfer, and this one here is nothing else than the frequency at which the photons are back and forth reflected. So now, of course, there is a difference in the force, and the difference in the force is due to the gravitational redshift, and so I get for the difference of the force this mass of the photon times little g. So the photon inside the cavity gives extra gravitational mass to the cavity. So therefore, if you put this cavity on a scale, the photons have more momentum transfer to the lower wall than to the upper wall, and that means you measure an additional weight, you measure additional gravitational mass, and the gravitational mass of the photon is due to the gravitational redshift. So I would actually put it like this: the only situations where photons do not have real mass is when we have a single traveling wave where everything moves at the speed of light in one direction, and that would mean the norm of the 4 vector of energy and momentum is truly 0. But in all other situations, you see how gravitational redshift, Doppler shift mean that the photon contributes to the inertial mass, to the gravitational mass, or to the mass whatever of the object for which we define the center of mass frame with a 0 momentum. Okay, well, so I hope I've now completely explained that it is accurate to talk about the mass of the photon, and that to define the kilogram by the mass of 1.47 times 10 to the 40 photons is physically correct, relativistically correct. You just have to explain what the photon mass is. And I found it an amazing teaching moment when I could explain to the president of a metrology institute why I think photons have mass. Okay, but this is the definition, and we always have to distinguish the concept of a definition to the realization. And I can't tell you how many popular write-ups about the new kilogram confound the definition of the kilogram with the realization in the watt balance or so. But let's now do the step from the conceptual definition, I'm done with that, to how is the kilogram realized? How can we now measure a kilogram in terms of the new definition? Well, let me first say you can never do that. To create 1 kilogram of photons requires 1 year of a medium-sized nuclear power plant. I mean, 1 kilogram of energy is just amazing. 1 kilogram, E equals mc squared, pure energy. But that means we should not try to implement it. But there is one possibility, and let me start with that. Instead of creating energy, we can take energy we have, massive objects we have, and annihilate them. So if you just want to follow me with a thought experiment, if we annihilate an electron-positron pair, it creates 2 gamma rays at this famous 511 keV energy, and this has a frequency of 1.2 times 10 to the 20 hertz. If you now measure the frequency of those gamma rays, and you can compare it directly, the frequency, to a cesium clock, and many people know that frequency comparisons in atomic physics using frequency combs can be done with a precision of 10 to the minus 18, which for all metrology is infinitely accurate because all other quantities can only be measured with 10 to the minus 8 or 10 to the minus 6 precision. Once we have something in frequency, it's super precisely measured and it can be traced back to the atomic clock. So therefore, if we are now measuring the frequency of this annihilation radiation with a frequency comb, we have directly determined the mass of the electron. So this shows how frequency measurements, and if you want to use this bridge, you can annihilate any particle you want if you measure its frequency, because h is now defined. You have determined its mass. So I can also say this is maybe how you can think about it, about the new kilogram. If you want to know, how heavy, what is your mass, how heavy you are, find your antibody, annihilate, and then ask somebody to measure the frequency of the annihilation radiation. This is how you can trace back your weight exactly to the new definition of the kilogram. And maybe there is a last moment of pride for you. But well, I'm working my way, by the way, towards how the kilogram is realized. But I like to have these conceptual steps. So we want to say mc squared is h nu, so we measure the rest frequency. If we measure a frequency measurement of that, we are done. We have determined the mass absolutely. But now, instead of mc squared, why do we need the rest energy? Couldn't we just measure the kinetic energy in a frequency measurement? And then we would also know the mass, provided we know the velocity or the momentum very, very precisely. It just happens, c is defined, so we know the speed of light with infinite precision, but if we can measure kinetic energy of an object where we know the velocity, this is equivalent, then we can pull out the mass. And the example for that is the spectroscopy of hydrogen. Some spectroscopy of hydrogen was pioneered by Dan Kleppner here at MIT. But let me just remind you of something we teach in our atomic physics class. The kinetic energy of the 1s electron is equal to the Rydberg constant via the virial theorem. The kinetic energy and the binding energy of the 1s electron are the same. But that means that the velocity, the RMS velocity of the 1s electron is the fine structure constant times the speed of light. And the fine structure constant is an extremely precisely known constant. It's E squared over H bar C. And this number, I've given it here in its full beauty, is so precisely known that it actually introduced negligible error here. So in other words, we can now, if we measure if we do hydrogen spectroscopy and determine the binding energy, and we measure sort of Balmer lines and Lyman alpha and whatever, we measure those lines, we pull out the Rydberg frequency. From the Rydberg energy or Rydberg frequency, the Rydberg constant, we actually get the mass of the electron. Even more precisely than annihilating the electron, because we don't have the frequency metrology for gamma rays, but we have wonderful frequency metrology for visible and UV lasers, which are used to perform spectroscopy of hydrogen. Okay, so this is how we move forward. We have a definition, but now we implement the definition of the new kilogram by doing spectroscopy of hydrogen. And through the Rydberg constant, we know now the mass of the electron. We still have a long way to go from the electron to the kilogram. But the next step is to use a Penning ion trap of the kind which Dave Pritchard pioneered for extremely precise mesh measurements. And we compare the cyclotron frequencies for an electron with the cyclotron frequency of an atomic ion, which is 5 orders of magnitude heavier. So we can measure the mass ratio very precisely. So now we are getting much closer. I first said the job is to count to 10 to the 40. And the answer is no, give up. You cannot count to 10 to the 40. But the story is the following. You don't want to do stupid counting. So if you win a big prize, $1 million, and the prize is given to you in pennies, would you count pennies? No. You would trade in the pennies against dollar bills, then you would trade in the dollar bills against $100 bills, and then maybe you start counting $100 bills. So you want to trade in first, you want to have multipliers that the counting becomes manageable. And what I told you is that instead of counting 10 to the 40, we have 3 multipliers in the realization of the new kilogram of 10 to the 5. We are using UV photons to do hydrogen spectroscopy instead of the cesium frequency, which is in the microwave range. And we are already 10 to the 5 times higher in the mass of those photons. Then we are using that to determine, well, not the mass of the electron, we are determining the mass of the electron, but scaled down with the fine structure constant squared. This is a ratio of the mass of the electron to the Rydberg constant. So we've gained another factor of 10 to the 5 because we know the knowledge of the fine structure constant. And then we measure the mass ratio of atoms and electrons in a Penning ion trap. So we have now already gotten, by trading in the small quantity, the 1 cent against the $100 bill, we've made some progress, and what we have to do now is we only have to count 10 to the 25. So let me tell you how people have counted 10 to the 25, and it was actually this technology, this amazing achievement, which enabled the new definition of the kilogram. So how do you count to 10 to the 25? Well, let's first do the math. If you would count at 50 millions per second, it will take the age of the universe until we count to 10 to the 25. So direct counting of 10 to the 25 is out of question. And to everybody in the audience and the students, this shows you how much 1 mole is. If you really want to count 1 mole of particles, you better, you have a hard time doing that before you graduate. But now how it's done. What the PTB, the German Metrology Institute, managed to do is to make one of the roundest spheres in the world. This is actually a sphere of that size. It's a silicon sphere, which is polished to within nanometer. They developed new polishing methods. They developed new interferometric methods to calibrate, to measure precisely the spherical surface to a large degree of precision. So now when they say they count the silicon atoms, they actually use this word. It's okay, but they're cheating a little bit because what they measure is by interferometric measurements, optical interferometry of the surface, they precisely measure the volume of the sphere. So now you see, maybe you don't have to count. If you know the volume of the sphere, And if you use a single crystal and precisely measure the lattice constant cube is the volume taken by a single atom. And if you know the volume of the sphere, you have actually in a smart way determined the number of atoms in this sphere. So this is the way how 10 to the 25 atoms in the silicon sphere were counted with a precision of 10 to the minus 8. This took them many, many years, because at that level of precision, you have to control surface roughness, you have to find new methods to characterize the isotopic abundance of silicon, you had to team up with Russian scientists to use isotopically enriched silicon-28, you had to correct for lattice defects and all that. This is really an amazing tour de force. But in the end, they have counted 10 to the 25 atoms. They have connected the mass of a single atom, as I mentioned before, determined by hydrogen spectroscopy, ion trap mass comparison and such. They have connected the mass of a single atom to the mass of 1 kilogram at the 10 to the minus 8 precision. And that now became better or comparable to the precision of comparisons of the original kilogram in Paris, and this enabled the new definition. Okay, for completeness, I've mentioned to you how we can determine mass if we precisely know the velocity of an object, and the example I gave you was hydrogen spectroscopy, where we know that the one s electron has a velocity which is exactly alpha, the fine structure constant, times the speed of light. But there is another way, and this uses this relation, and this is actually realized in atom interferometry, where the momentum is precisely known because it is the momentum transfer to the recoil of the absorption of a photon. So this is now a second route which is comparable or even slightly better now in precision to the hydrogen spectroscopy. But let's move on now to the second method which is used to realize the kilogram, and this is called the watt balance. Well, I've talked to many people. Eventually, talking about the kilogram became one of my favorite subjects when I had dinner with colleagues, or because it's so interesting. It gets you into so many interesting questions of physics, like the mass of a photon. How do you count and all that? Now, the watt balance, everybody I talked to had heard about the watt balance, but when I asked somebody, can you explain it to you? Oh yeah, it's complicated, I read it somewhere, there are some equations, and if you look at the website of the people who have the best watt balances, it is the NIST here in the US, and it is the Canadian NRC, Canadian Research Institute. Yeah, you read the equation, something comes out, and you say, okay, that works. But now I want to try to explain to you in fundamental physics terms how the watt balance works. And I was actually first confused when I had, what I did so far is sort of more in my comfort zone. It was about hydrogen spectroscopy, atomic physics, and also I've never done it myself. I mentioned the names of Dan Kleppner, hydrogen spectroscopy, Dave Pritchard, ion mass measurements. So I learned it just through the skin by being here at MIT. But then I said, now I have to explain the watt balance. And I'm actually happy I found a way where I can show you that the watt balance is analogous to what I've told you before. Because what did I tell you before? A kilogram is an elementary mass of a photon, and maybe we scale it up by a few times 10 to the 5, but then it comes to counting. And what I want to tell you now is that the watt balance is similar. It has a frequency, but this frequency is a Josephson frequency to measure a voltage. We are getting there. And then you can count the many electrons in a current. So you see the similarity. A microscopic energy measurement through frequency, and then you have to count. So what is the watt balance? Well, before I explain the Watt balance, I need one equation, and that is, so far I've told you that we measure mechanical energy, mc square, the rest energy, 1/2 mv square, kinetic energy. The Watt balance actually does the derivative. It measures power instead of energy. So I just want to remind you that the derivative of mechanical energy is mass times velocity times acceleration. And, well, I'm always trying to teach the derivative of kinetic energy is the same as the derivative of potential energy in the gravitational field. So mvg is now the mechanical energy or the derivative of mechanical energy we want to measure. So what happens in a Watt balance? A Watt balance has an object, let's say mass of 1 kilogram, but then you have a coil and you run current through the coil in an inhomogeneous magnetic field. And you make sure, if you have a current and a magnetic field, you get a Lorentz force. And now what you do is you levitate an object by running a current through the coil and having an inhomogeneous magnetic field. So you have an object, 1 kilogram with a coil, there's a magnetic field around it, and if you run just the right amount of current through it, this 1 kilogram is levitated. Balance, levitation, that's what a balance is. So you levitate the object. But now, if the object is levitated, gravitational force is compensated, you can move it at a velocity v without any external force because it's force-free when it's levitated. But that means when you move it up, you gain mechanical energy, potential energy at a rate mgv, but you're not putting any force in it, and then energy conservation comes. This mechanical energy per unit time must come from running the current through the coil. It must come from an electric power where I is the current we run and U is the voltage which is induced by Faraday's law because you move a conductor through a magnetic field. So this is just energy conservation. The rate at which you gain mechanical power, because when you move the coil, you're not doing any work because the coil is levitated, must be equal to the electrical power. And that's why it's called Watt balance. Watt is the unit of electrical power, and this is now equal to the mechanical power. And it's a fantastic instrument. It operates in vacuum. You have the mass, you have coils, you move it, you have a motor. Of course, you have to measure the velocity interferometrically. You have to do a precise determination of the Earth acceleration g. So there is a lot of very advanced technology behind it. But in the end, this is our equation. mgv, the rate of mechanical power, is electrical power. And g can be determined very precisely by interferometrically tracing a falling object. Velocity can be measured by looking at the moving object with an interferometer. And now the question is, how do we measure current and voltage? Well, first I have to say the voltage, the induced voltage, is actually measured in a separate experiment where you have an open circuit because you want to avoid the resistive voltage due to the current. So you measure the current for levitation and you measure the induced voltage separately. That's number one. And number two is the most precise way to measure voltages is done via Josephson junction. I cannot explain it more than just stating that if you have two superconductors and you apply a voltage across them, then you create microwave frequency which is proportional to the voltage. So now you can measure voltages via frequency because the Josephson junction, or you can irradiate a Josephson junction with a certain frequency, and what you measure is a precise voltage. And as you know, frequency is what we can measure accurately. So we can make a frequency measurement of the voltage, and this can be directly traced back by frequency comparison to our cesium atomic clock. Okay, so this takes care of the current. And now what about, of the voltage. What about the current? Now in principle, and now I'm back to counting, A current can be measured by a single electron pump, and you can count single electrons. You can have you can shuffle single electrons and create a current up to 100 picoamp and count every single electron. So therefore, the current can be actually counted by the number of electrons per unit time times the charge of the electron. So therefore, the electrical power is nothing else than the Josephson frequency times the counting of electrons. And here is now the mass traced back to h by frequency times counting. So in that sense, what I've explained you so far with the Watt balance is somewhat analogous to the silicon sphere. You measure a frequency either spectroscopically or here through the Josephson junction, and then you count. And by the way how I've so far explained the Watt balance, by using this equation for power, Josephson frequency, the potential energy of an electron when it goes around, times the number of electrons per unit time, does not require any concept of electrical quantities, resistance, voltage or current, or even definition of the elementary charge. So you can conceptualize the Watt balance without going into the electrical sector of units, in principle. But in practice, the more precise method to measure current is use a quantum Hall device, which has quantum Hall plateaus at a very fundamental resistance called the quantum Hall resistance or the von Klitzing constant. So the best way to measure a current is not to count electrons, but run this current through the von Klitzing resistor, which is precisely known. Then you get a voltage, and the voltage, as I've already explained to you, can be super precisely measured through a Josephson frequency. I have to say I'm a little bit in awe with this quantum Hall trick, using the quantum Hall resistance, because it means now we can measure absolutely the mass of a kilogram in this mass balance through the knowledge of Planck's quantum without counting at all. So in what I've explained to you before, we have to eventually count to bridge the gap between a microscopic definition and a macroscopic kilogram. But if you measure the current through the quantum Hall effect, no counting is needed because you are using a macroscopic quantum effect, the quantum Hall effect, which connects the microscopic to the macroscopic world. I really find that remarkable. Okay, so where are we? I've explained to you the fundamental definition of the kilogram, and I've explained to you the two methods, how h was measured most precisely, but the moment h is defined, this becomes now the method to realize the kilogram in the most precise way. Let me just spend a few minutes to talk about the other units, which are actually much simpler to explain. It's really the kilogram which has been the challenge. We also have redefined the mole, we have redefined the Kelvin, and we have redefined the ampere. But this is easy to explain. The new definition for charge and current is simply done by defining now the charge of the electron or the elementary charge as a specified number. And then, of course, 1 coulomb is the inverse of this number in the number of electrons, and the current 1 ampere is 1 coulomb per second. The mole has also been redefined. It's now defined by having a specified number of Avogadro's constant. So Avogadro's constant no longer has an uncertainty, it is defined. And finally, temperature is now defined, no longer by the triple point of water, but is defined by defining the Boltzmann constant. So the Boltzmann constant has no uncertainty anymore, it is defined, and this defines the Kelvin scale of temperature. Which is actually very nice. Actually, teaching 8044, I realized, why do we really need temperature? If we would specify temperature in energy, just folding in the Boltzmann constant, everything would be the same. It's just that somebody started out with temperature, and now for historical reasons we are holding on to temperature. But if we had decided to call temperature times Boltzmann constant, which is an energy you set to determine temperature, today it's 10 to the minus, whatever, 10 to the minus 20 joule. It's really hot. I mean, this is what we would say. So we could completely avoid using temperature as a separate unit. Now, just to fill that in, with this fundamental definition of K. Boltzmann, we can now measure the temperature of a gas by measuring, of course, its average kinetic energy. But the average kinetic energy is directly related to the speed of sound. So if you measure the speed of sound, you have a direct measure of temperature. So what are the advantages of defining those new units? Well, one is it's no longer related to artifacts. It can be realized everywhere in the world. Any progress in counting atoms, in frequency metrology or such, can now improve the realization of those units, because it's now open. Any method which can connect the mass of something to age can become a new method and is an absolute way of measuring masses. The important thing is also for the kilogram and the Kelvin. The kilogram was defined at 1 kilogram. And if you work in the pharmaceutical industry and you have a few microgram of a very, very expensive substance, you could absolutely determine the microgram only by taking the kilogram and in a complicated measurement procedure go from kilogram to 100 gram to 10 gram to 1 gram. It's called a step-down procedure, which requires many intermediate standards and many measurements. But now you can just operate a Kibble balance for very, very small mass, or when the masses become very small, you can also use an electrostatic balance. So there is a way now of directly implementing the SI definition, not just at the kilogram scale, but at the milligram and microgram scale. And similarly, temperature was defined, well, by the triple point of water at 273 Kelvin. If you were interested in thermometry in millikelvin, you had to sort of scale it down. But now, in principle, you can measure the speed of sound of a very cold gas, and you have absolute thermometry. This is actually what we do in my labs and Martin Zwirlein's lab with nano-Kelvin gases. We look at the speed of sound, or we look at the thermal velocity of those gases, and now, eventually, we are really doing the absolute definition of temperature because the Boltzmann constant is defined. Okay, I'm a little bit over time, but I have just a few more slides. So I started out with Planck and said Planck really was the visionary. He talked about defining units through fundamental constants, no longer having artifacts, being able to communicate with extraterrestrials. This was his vision. So let me raise the question, what would Planck think today? Would he be satisfied? Well, not quite. Because here in his paper, he didn't like to single out, let's say, an electron or the cesium atom, and he gave the example of the sodium, because sodium was very popular. It gave wonderful yellow light. And he said, if we would use the sodium wavelengths to determine lengths, of course, this would be a quantum device, it would be reproducible, it would be an atomic definition. But he said, no, this would be arbitrary. We would single out a special element, and it is possible that there are some, I don't know, other places where sodium is not abundant or so. So he didn't like that the definition of units was connected to a real particle, even if the real particle is a cesium atom. And what he rather wanted is, he wanted to just use fundamental constant, and indeed, you can eliminate the cesium atom, you can eliminate the definition of a second by defining the gravitational constant G. So this would no longer single out any particle made by nature. And now you can speculate. We talk a lot about string theories and multiverses and such. If there were another universe which doesn't have the standard model particles, but it has the same laws of physics with the same speed of light, the same age, and the same big G, if we would place our units on G, H, and C as Planck suggested, we could still communicate to this world without pointing to any elementary or composite particle in the standard model. But This is not really feasible because everything which is related to big G has currently a measurement uncertainty of 10 to the minus 4. Big G is the fundamental constant which has the largest uncertainty because gravitational effects are weak. So following Planck's suggestion would really ruin the accuracy of our system of fundamental units, and so therefore for a while, we are still holding on to one specific atom, which is now the cesium atom, and I'm sure it will soon be replaced by an optical frequency standard. So this morning, when I prepared for the talk, I looked at the web and looked at some news. And you see what? I came across one website which has the following definition of the kilogram. The kilogram is equal to the weight, well, weight and mass, let's forgive them, of 1.47 times 10 to the 40 photons. And I would be completely surprised if this report, which is one sentence, 100% correct and understandable, I'm almost 100% certain that the person who wrote it was reading the MIT press release, where the way how I explain the kilogram is presented. So eventually, if you're interested, I'm really trying to, as a science communicator, to make science transparent and simple. I've written a guide for teachers and students, and I would actually hope that the new definition of the kilogram would be a teaching moment for high school, that every high school teacher in the country would explain to his or her science class what the kilogram is and use it as a wonderful opportunity to also talk about the mass of the photon. There's also a more detailed popular article, and I forgot to mention that actually my partner in crime here is Alan Jamieson, postdoc, and many of the ideas I presented here were developed in discussions with him. So those resources will be on the website later today. So now I know my time is over. I would have covered a little bit more, but maybe these are questions you can ask me during the reception or in the question and answer. So here are a few questions which, if you don't know them, you better do your homework, because the units is the basis for physics, for science and technology. Is 1 mole of carbon still exactly 12 grams? Does the vacuum permeability, which is 4 pi 10 to the minus 7, does it have now an uncertainty? Is there an error bar on 4 pi now? Or if you do a precision quantum Hall experiment, like we have people here at MIT who do precision Hall measurements, the Hall resistance is now defined. So if the resistance is defined, what are they measuring? Or is it really true that all of a sudden from yesterday to today, the electron mass is now better known by a big factor? Or a lot of people talk about the change of fundamental constant. How can fundamental constants change when they are defined? Anyway, if you want to take the quiz, tell me how you're doing on it.
Thank you. I think that was one of the most memorable talks I've heard in this room. So we have a few minutes for maybe 2 or 3 questions from the audience. And you can, yeah.
Oh, let me flash the
Just call
resources.
out the number of the question. Yes, Veet.
My question shows that I didn't follow the logic. Definition. What is the mass of a piece of matter?
Say again?
In your definition, what is the mass of a piece of uranium platinum carries and how was it measured?
Okay, the piece of the platinum iridium alloy in Paris is 1 kilogram. Actually, whatever it is, this is 1 kilogram. If it loses mass, it's still 1 kilogram, because the kilogram was defined by the mass of this specific object. And it was fabricated in the following way. The original definition of the kilogram was that it is the mass of water in a cube, 10 centimeter times 10 centimeter, a liter of water. And then I think, because it became somewhat harder to precisely prepare a liter of water, they created this artifact, this special piece of metal, and made it as accurately as they could match the mass of 1 liter of water. So it is 1 kilogram. Okay, what happens is the following. Number one is the kilogram in Paris by definition has 1 kilogram, and the mother of all kilograms is now this cylinder in Paris. And what people now did is, until now, they had to use, every national institute has a copy of this kilogram. So eventually, the German PTB and the American NIST and the Canadian Metrology Institute, when they measured age, when they got the most precise value of age in kilogram meter, so what is it, meter square per second squared, when they determined age, they needed in their measurement at least a chain where they traced their measurement back to the kilogram. So what we had was 1 kilogram, which was without any error, and the measurement of age was done, and there was an error bar which reflected how you connected the kilogram in Paris to the measurement device in Braunschweig and Gaithersburg. But then, as of today, we turn things around. We say this error bar disappears, and suddenly the kilogram in Paris, when we compare it to the silicon sphere or put this kilogram into a watt balance, every time we measure the kilogram now, the special kilogram in Paris, it will have a 10 microgram error. So this is what you do, is you push the precision in measurement traced back to the old standard, but then you simply say, this becomes now the definition, and suddenly what used to be the standard has an uncertainty.
So the number of photons was tagged to the central value of the...
Yeah, exactly. You tried as precisely to make the new definition seamless. You had a kilogram and you can only measure it to within 10 microgram. But you define h bar, or the number of photons, which is 1 kilogram, that it is as precisely the kilogram we have in Paris, as precisely as the kilogram in Paris can be measured. And that means it now opens for the future to create kilogram pieces, probably not out of iridium because of maybe the hydrogen diffusing in and out, but maybe of a single crystal of silicon, which are maybe then in the future 10 times more precise, 10 times more reproducible than the kilogram in Paris. But
Okay,
right now, we are not gaining any precision at the kilogram scale because the tipping point in the definition came when the uncertainty in age and the reproducibility of the original kilogram were comparable.
I think we'll give the last word to Dave Pritchard.
Yeah, so as physicists, we have almost an article of faith that we believe the fundamental constants don't change with time. Well, not quite, because there are a number of experiments which actually explore this. But now that we've defined the fundamental constants to measure the measurement, how do we keep up with this tradition of seeing if the fundamental constants are changing?
That's a good question. So let me put it this way. We have a proton mass, we have an electron mass, we have age, we have many fundamental constants. And when you want to talk about the change of fundamental constant, you need actually 2 measurements. You have to compare 2 fundamental constants. If a single mass changes, it could simply because your definition of the kilogram has some drifts. For instance, the drift which we had right now with the kilogram in Paris. So when we say, or let me put it this way, there are certain fundamental constants which are metrological. They define the units. And they cannot change by definition because you need a definition to measure anything. So when we say we can now check the drift of fundamental constants, we can only look at constants which I would say are dimensionless, the mass of the electron to the mass of the proton. If that changes, they were both traced back. There is a change in our universe, and the masses are not constant. So in other words, you have to really distinguish between fundamental constants which are metrological and fundamental constants which, the metrological fundamental constant is the minimum fundamental constant you just need to define a system of units. And then every other fundamental constant relative to those, you can now measure if they are changing. And there's a possibility, and there's a long tradition in our field, to have precise atomic clocks and see if 2 very precise atomic clocks show a drift relative to each other, which would really mean that in our cosmological evolution, the fundamental constants are changing.
Okay, let's thank Wolfgang again.